The fovea centralis is a small depression within the macula luda that contains the densest concentration of cones. Now when you're looking back here on the retina, there is an area called the fovea centralis, and the fovea centralis is your focal point. A small depression, here's the fovea centralis here in the retina, and it's a small depression within the macula luda, which is just an area around that fovea centralis, both of which contain cones. However, the fovea centralis contains the densest concentration of cones. So it's the area of highest visual acuity or sharpness of vision. It's your focal point. So whenever you're staring at something, that image that you're looking at is coming right in and stimulating the cones of your fovea centralis. These foveocones are a little different than the regular cones in that they have very long, slender bodies. Blood vessels and other retinal cells are displaced to the side rather than directly on top of the cones. This allows light to pass unimpeded onto the cones, such as this right here. Here you have your ganglion cells, here's your bipolar cells, and then here are the rods and cones with the discs that need to be stimulated when light comes through this. So light has to come all the way through in between your ganglion cells, your bipolar cells to stimulate these photopigments. In the area of the fovea centralis, this area, the bipolar cells and ganglion cells, are pulled to the side. So it doesn't impede light coming in to stimulate these discs back here. So shown here, here's light coming in. Here are these cones in these areas. As light comes in, it stimulates this, and it doesn't have to go, there's no impedance from these bipolar cells and ganglion cells. And this is what it looks like in an actual microscopic slide, is that you can see here's a fovea centralis, and then all along in here, here's your ganglion cell layer, here's your bipolar cell layer. They're pulled off to the side so no light impedance as that light comes in and stimulates your focal point or your fovea centralis. Here's your fovea centralis here. Here's the optic nerve where that is going to come out of the eye. Blood vessels are coming in. Veins are coming out. Arteries are going in. We call this area your optic disc or blind spot because you have no photoreceptors in this area. Here's an image of your retina looking through the pupil. There's your fovea centralis. The macula luda is around the fovea centralis. Macula luda contains only cones. Fovea centralis contains only cones, or central fovea is another term for it. The difference, the fovea centralis has the greatest concentration of cones. Highly concentrated in the fovea centralis, whereas the macula luda has cones, but it's not as concentrated. Then when you get out from the macula luda, this area here has both rods and cones. You have other retinal cells. You have bipolar cells. They're going to transmit the signal from the photoreceptors to the ganglion cell layer, shown here. Here are your rods and cones. Here are your bipolar cells. They're going to take impulses from your rods and cones and transmit those to the ganglion cells. The ganglion cell, or ganglion cell layer, these axons from here, when they get stimulated, they're going to send impulses along their axons. These are the axons that exit out of the eyeball to become the optic disc. So shown here, that optic disc or blind spot is in this area. Doesn't have rods, doesn't have cones. This is where the information on those nerves is taken out of the eye. Fovea centralis, as well as the macula luda around it. And then these are all the blood vessels in the choroid. And right here where the blood vessels come into the eye and exit the eye, as well as an absence of rods and cones, you have what's called the optic disc, or the blind spot. So the optic disc is a region where axons and neurons exit the eyeball as the optic nerve. The area contains no rods or cones, and thus we cannot see an image that strikes this region, and hence the name blind spot. It's right here where the optic nerve forms. In your notes, you're going to see a site that you can go to where there are exercises that allow you, or activities allow you to find your blind spot. I highly advise you go to this and check it out. It's absolutely amazing, especially for date night. You can do this on a little 3x5 card. You put a little plus in a box, and then you bring this slowly up to your face, and then you'll be able to find your blind spot. Follow the directions that are on that site, and you will be impressed. And there's some other visual activities there as well. There's a condition known as age-related macular degeneration, and this can have devastating effects on vision. As you can see here, here's an image with this taken out where you can't see anything in this area due to this condition. AMD, or age-related macular degeneration, is a leading cause of blindness in people over the age of 60. There are two major types of age-related macular degeneration. You have what's called dry and wet macular degeneration, and that depends on the blood vessels basically in the area. In dry or non-neovascular AMD, it's the most common type and accounts for about 90% of the cases. In this situation, the person is going to produce drusen, which is a waste product of photoreceptors. So remember how we talked about these discs, and as they get shed, the pigment epithelium phagocytoses those? Well, if it's not working correctly, it's not phagocytosing these, the disc, the old disc, can accumulate in the area as well as other debris, and we call that altogether, we call that drusen. And it can accumulate between the retina and the choroid, and it can cause visual problems. However, it usually progresses very, very slowly, and it rarely progresses to legal blindness, this dry AMD. Now, wet or neovascular AMD is the least common. It affects about 10% of all cases. And here you have the accumulation of drusen, as I described before. You also, in addition to this, have abnormal blood vessel growth, which occurs underneath the retina in the choroid layer. So here is your choroid layer, here's your retina with the photoreceptors, and you just get lots and lots of blood vessels growing in this area. As the name implies, the appearance is wet. Blood and serum leak out of the new frail blood vessels because you're producing lots and lots of blood vessels in people who have wet AMD. For some reason, they're making lots of blood vessels. They don't know exactly why. This can cause visual distortions and permanent tissue damage. It can also result in a retinal detachment and scarring, causing significant loss of vision, and many times it can cause legal blindness. Here's an image of wet macular degeneration, accumulation of blood vessels and serum that can lift the retina off the back layer of the choroid. Now the lens lies posterior to the iris, as shown here, and the pupil, which is the opening, and basically it's going to function to focus images on the retina in the back of the eye, as we previously talked about. It's held in position by these zonular fibers or suspensory ligaments that are attached to the lens capsule, and the capsule goes around the lens. The lens consists of transparent elastic proteins called crystallins. As shown here, the lens fibers are those crystallins, and they're arranged like layers of an onion. And we have lab, I'll do a dissection on a sheep's eye, and we'll take out the lens and I'll show you how these lens fibers or crystalline proteins are arranged. When you look at the interior of the eye, the lens divides the interior of the eye into two cavities. You have the anterior cavity, which consists of everywhere where you have this aqueous humor. So all of this is your anterior cavity. And then you have your posterior cavity, or your vitreous chamber, which has a fluid called the vitreous body. We'd already previously discussed that aqueous humor is produced by the ciliary processes, and that's going to come flowing through, nourishing the lens and the avascular cornea, nourishing the avascular lens and avascular cornea, and it's going to be drained into these sclerovenous sinus or canal schlemm. So the anterior is anterior to the lens, and it continually produces aqueous humor secreted by the ciliary processes, flows through the anterior cavity and is drained into the sclerovenous sinus or canal schlemm, and it's going to help maintain eye shape and nourishes the avascular lens and cornea. Posterior cavity, or vitreous chamber, lies between your lens here and your retina. And the vitreous humor is a jelly-like fluid that fills this area. Basically looks like raw egg white. It's formed during embryonic development, and it's real viscous in consistency. Now, aqueous humor is real watery in consistency. This is real jelly-like in consistency, that vitreous body or humor. It's formed during embryonic development, and it's not replaced thereafter. Now, some sources will say it's replaced, but it's replaced very, very slowly. Other resources say once you're born with this is the amount that you're going to have for the rest of your life. The function of this is that it's going to contribute to intraocular pressure, and it helps prevent the eyeball from collapsing. So without this vitreous humor in here, the eyeball would just collapse. It helps to hold the retina flush up against this choroid There are some attachments of the retina, but certainly this vitreous humor is going to help hold it up against it. And have you ever experienced these eye floaters that you see out in your visual field? Well, these eye floaters are found within this vitreous humor here. And what you're basically looking at is a shadow of the floater on your retina. So out here you have these floaters, and then they can cast shadows as light comes in onto your retina. As you age, that gel-like vitreous humor, composed of millions of fine collagen fibers, they can shrink and they can tend to clump together. And you can also have various other debris in there, and that is going to cast shadows onto your retina, and you perceive these shadows as eye floaters. Floaters move as your eyes move, and they appear to zoom away when you look directly at them, or they can drift slowly when your eyes stop moving. Although they can happen at any age, they most often occur in ages between 50 and 75. I'd like to show you now is a video from TEDMed, and it discusses eye floaters as well as other eye phenomenon.
Have you ever noticed something swimming in your field of vision? It may look like a tiny worm or a transparent blob, and whenever you try to get a closer look, it disappears, only to reappear as soon as you shift your glance. But don't go rinsing out your eyes. What you are seeing is a common phenomenon known as a floater. The scientific name for these objects is Muscae volitantes, Latin for flying flies, and true to their name, they can be somewhat annoying. But they're not actually bugs or any kind of external objects at all. Rather, they exist inside your eyeball. Floaters may seem to be alive since they move and change shape, but they are not alive. Floaters are tiny objects that cast shadows on the retina, the light-sensitive tissue at the back of your eye. They might be bits of tissue, red blood cells, or clumps of protein. And because they're suspended within the vitreous humor, the gel-like liquid that fills the inside of your eye, floaters drift along with your eye movements and seem to bounce a little when your eye stops. Floaters may be only barely distinguishable most of the time. They become more visible the closer they are to the retina, just as holding your hand closer to a table with an overhead light will result in a more sharply defined shadow. And floaters are particularly noticeable when you are looking at a uniform bright surface, like a blank computer screen, snow, or a clear sky, where the consistency of the background makes them easier to distinguish. The brighter the light is, the more your pupil contracts. This has an effect similar to replacing a large diffuse light fixture with a single overhead light bulb, which also makes the shadow appear clearer. There is another visual phenomenon that looks similar to floaters, but is in fact unrelated. If you've seen tiny dots of light darting about when looking at a bright blue sky, you've experienced what is known as the blue field entoptic phenomenon. In some ways, this is the opposite of seeing floaters. Here, you are not seeing shadows, but little moving windows letting light through to your retina. The windows are actually caused by white blood cells moving through the capillaries along your retina surface. These leukocytes can be so large that they nearly fill a capillary, causing a plasma space to open up in front of them. Because the space and the white blood cells are both more transparent to blue light than the red blood cells normally present in capillaries, we see a moving dot of light wherever this happens, following the paths of your capillaries and moving in time with your pulse. Under ideal viewing conditions, you might even see what looks like a dark tail following the dot. This is the red blood cells that have bunched up behind the leukocyte. Some science museums have an exhibit which consists of a screen of blue light, allowing you to see these blue sky sprites much more clearly than you normally would. While everybody's eyes experience these sort of effects, the number and type vary greatly. In the case of floaters, they often go unnoticed as our brain learns to ignore them. However, abnormally numerous or large floaters that interfere with vision may be a sign of a more serious condition, requiring immediate medical treatment. But the majority of the time, entoptic phenomena, such as floaters and blue sky sprites, are just a gentle reminder that what we think we see depends just as much on our biology and minds as it does on the external world.